Hello, everybody. My name is Fabian Leal Villaseca. I'm very happy to be here. I get to talk to you about my research. Well, this is my work for my PhD. I've been supervised by Mark Lindsay at Cripps and Mark Jessel from UWA. And well, I've been working on deep learning for spatial interpolation in geostats. And well, I'll tell you all about it now. I have an overview for a structure here. I'm just going to tell you the aim first so you get a bit of an idea of what we're trying to achieve here. Then motivation, methods, results. So why do we want to do deep learning in spatial interpolation in geostats? Well, the reason is we've all seen how successful these models have been in other fields, how accurate, how scalable. But it is not the most popular in this particular niche because there's a few barriers that prevent it from being very practical. I would say there's three barriers. One I didn't address in this study, but it's related to uncertainty quantification and its difficulties with deep learning. And the two that we did address, well, one big one that has been mentioned a lot in this conference is the challenge of interpretability, which is especially important in some applications in the geosciences. And well, the other challenge is more specific to spatial interpolation and how deep learning learns with the spatial coordinates. But I'll talk more about that soon. So first, motivation. So why, in more detail, why did we get this idea of using deep learning in this specific niche? Quick rundown of spatial interpolation. I'm sure most of you are familiar. So we have some phenomena that we can plot in space. In this example, it's elevation. So we have a few values. Usually it's not many. And with what we have, we need to estimate what's in the middle or what's unknown, right? There's lots of methods for this. A very basic one is inverse distance weighing, where if you want to know the value of an unknown sample, say that's question mark there, and you know some adjacent values, you simply do a weighted sum of those values, and in the case of this inverse distance weighting, it's just weighted by the inverse of the distance. So the closer it is, the more weight it has, which is very logical. But you can get more sophisticated with, well, the quintessential method in geostats, which is Kriging, which in essence is also a weighted sum, but the weights are calculated in a bit of a more sophisticated manner. So Kriging is also called the spatial best linear unbiased predictor, which when you express mathematically, you get an equation that when you play around with it, you end up with a covariance matrix and some weights. And long story short, in order to calculate the weights, you need to invert this covariance matrix, which is very computationally expensive. And well, this is a common problem that has been worked on a lot in the field of geostats. So basically developing models around DeepKriging or bettering DeepKriging in some way to make it more scalable. And that has been done with some success. For example, fixed rank Kriging does a very good job at dealing with large volumes of data. But there's one thing that hasn't been dealt with as much in the field of geostats, and that's when there's presence of additional covariates in addition to having large volumes of data. So usually what is done in those cases is apply a linear regression and then combine that with a spatial model, whatever it is. But the problem with that is that doesn't capture the whole complexity of the data that you can actually use when you have more variables available. So that's how we thought about deep neural nets, because, well, that's what they're good at. And that's what's made them so successful in many other fields, especially the ones that have been mentioned a lot in this conference, so computer vision and natural language processing. And well, what we're trying to do here is see if it can also be successful in other less popular niches, such as interpolation and geostats. So, as I mentioned earlier, there's a few barriers to that. Interpretability is always a problem with deep neural nets, but in some fields it doesn't matter as much as in geostats or in some geosciences. Mainly because sometimes you have to make an important decision based on the predictions that you make, and you sort of want to understand the model that you're using if you're going to make a big decision based on it. So usually, well, deep learning models can't be trusted if you don't know how they work. And well, the other issue is that basically a regular deep neural net is not designed to capture spatial dependencies, and so the outperformance that you get from using deep learning is not as much as you would expect if you're going to use such a complicated method. So we're going to tackle those two things in the methodology section using, well, these tools. We're going to use DeepKriging, which is a model that was not developed by us, but is central to the study. And then we're going to attempt to interpret DeepKriging with a method that was, well, an adaptation that we made of a common method called Shapley values. And, well, I'm going to show all that in a case study. And, well, I promise there'll be some geology in that. So, well, DeepKriging, in layman terms, is a deep neural net that is designed to do spatial interpolation for specifically geostatistical data. So, for example, convolution neural nets are specialized also in spatial data, but when it's more dense, such as images and whatnot. In this case, this one's specialized for when data is very expensive and we only have few bits, so very sparse data sets. Well, what Chen found when he developed DeepKriging was that using the raw coordinates, such as X, Y, Z coordinates or latitude, longitude, the model would not learn the spatial dependencies as well as if you did an expansion. Well, he's very into many forms of kriging, so don't ask me how he got the idea to the expansion, but there is a theoretical basis as to how he got to that. And basically what he does is, instead of inputting X, Y, Z coordinates into the deep learning model, you expand it into a big number of basis functions, and that helps the model learn the spatial dependencies better. And this is all backed by a mathematical theorem called Carhoon-Leal theorem, or expansion, which allows you to expand the feature space in that way. So that last line would be our new estimator, which is defined recursively. So it's the last layer of the neural net. But that's a bit ugly, so I'll just show you a visual representation of what this neural net would look like. So it's just a normal, fully connected deep neural net, but the input is what's special here, because those x's would represent any covariate that we're using, but the phi's represent the basis functions that we expanded the x, y, z coordinates from. And that's just the real code, so you get an idea of how big the actual model is. And, well, obviously this model is gigantic and very complicated and hard to interpret. So the challenge here is, how are we going to do that now that we made it even worse by expanding the feature space, right? So, well, in comes Shapley values. Just going to describe this very quickly. Shapley values are an attribution method, so what they do is assign credit or blame to the features as to how they mattered towards the final prediction. And, well, I'm going to first explain a simpler case because it's a bit messy. The Shapley value is the full equation. So we're going to start with a simple case of, think of a linear regression or any additive model where there's no feature interaction. So what you can do to measure the importance of a feature, say feature J, you can just train a predictor on the full data set and then train a predictor on the full data set, but without that feature J that you want to measure. and then you do predictions with both those predictors, both those estimators. And the difference between those predictions is going to be the impact that feature J was originally having on the prediction, right? Then you get the delta. And this works well in that specific case with when everything's linear and no feature interactions. When there's feature interactions, it absolutely does not work at all. So you have to come up with something new, and that's, well, obviously our case of a deep neural net is the opposite end of what a linear regression would be. We have absolutely a mess in the sense of the feature interaction is quite complex. So we need to account for that, and what we do here is we do this same exercise of removing feature J and comparing, but we do it for every possible subset in the feature space. Okay, so that way we know how feature J contributes associated to each subset in the feature space. And, well, the full formula for Shapley values is coming, so remember that delta there. It's going to be in the equation. So that's omega J in the top is the formula to obtain the Shapley value for feature J, and then that S0 just represents some location in space. So it's basically a weighted sum over all the possible subsets in the feature space of that delta that I just showed. And, well, the problem with this, for us, specifically in our model with spoiler 493 features, is that you have to evaluate 2 to the power of the number of features to calculate the Shapley value, which is obviously intractable if we have that gigantic number. So what we came up with is a modification of the original Shapley value algorithm where we group together the features. So instead now we're calculating the importance of groups of features. But the only features that we're going to group together are the basis functions that we expanded upon, because one, we don't really care about the individual importance of each basis function. We care about the whole lot, because that represents the importance of the location in space. And two, it allows us to actually run the model, because if we don't do that, we can't. So that reduces the evaluations to 2 to the power of 6. So now we can do it. And we apply all this to a case study. In mine in Finland, we do dry bulk rock density estimation. So it's a resource estimation exercise where instead of calculating the R grade, we're doing density because we think it's an overlooked part of the process. So we wanted to do that. We have a lot of features, 161, a lot of data, but after cleaning, after removing the missing values and all that, we ended up with 2,600 2-meter intervals across 35 holes. So we're doing interpolation on that. We have 9 features. 3 of those are the coordinates, so actually 6 additional covariates. And, well, one of them would be the target variable, so only 5 covariates. And the experiments that we're going to do is first compare DeepKriging to benchmark models to see how accurate it is and how the 3D model looks like. And, hopefully from that we get that it is more accurate, because that's the whole point of using it. And second, we do the batch Shapley algorithm on DeepKriging to try to understand how it's working. So, this is the whole framework, the rock with some features, the feature expansion, DeepKriging, prediction, and then interpret that prediction. So results, first, the comparisons. I don't know how I am on time, but... Okay, so long story short here, DeepKriging does outperform in the purely spatial case even, which was the hardest case, because it doesn't have the advantage of the multivariates where Kriging would be weaker. And we also don't have that many points in the data set, so I think it's a fair comparison, and it completely outperformed. So that's good. This is what the the real data looks like in the top left. In the top right, we have Kriging, which, well, as usual, sticks to safe predictions close to the mean, and then DeepKriging, which really resembles a bit more what the actual real data looks like. So, yeah. Now I'm going to move on to Shapley values. So, how do we interpret what happened in the DeepKriging model? We're going to first look at one point in space and see how we got to that point. So here we're looking at one point that was predicted as density of 4.585. And what we're seeing here in the x-axis is density. In the y-axis, we have all the covariates that we used to do the prediction, and the phi represents, well, the basis functions that represent the spatial component of the model. So the width of those bars represents how important each feature is according to Shapley values. And the good thing about these values is that they use the same unit as the predictions we're making. So we can actually measure that, for example, phi here with that big bar accounted for 1 gram per centimeter cubed of the prediction, and so on. And another interesting property here is that the sum of the Shapley values equals the difference between the prediction that we're looking at and the expected prediction. So basically, you start with the expected prediction that you would have without any features, so that just the mean of the data that you have. And then with each feature, you add a little or subtract a little bit to that. And the Shapley values tells us how much each feature contributes. We can also plot the Shapley values in a more general manner. So here I'm plotting all the Shapley values of all the test set that I showed earlier. And well, we can observe here, looking at the top feature, the phi's, is that the spatial component is the most important, which, well, we don't need Shapley values to know that, but it confirms that it's doing a good job. Usually it tends to be the most important, either contributing positively or negatively to the predictions. And here I also plotted with color codes for the feature values. So you can also get some more sophisticated analysis if you look at how the feature values vary with respect to the Shapley values, where there's a clear pattern with chromium, but very hard to interpret. I'm not claiming to know why this happened, but there are clear patterns. Another thing that we did was we plotted the largest Shapley value for each prediction that was made. We plotted in 3D, so the largest of these bars, taking out the spatial component because that would always win. And then we would plot, the one who won in each prediction. And to the right is just lithologies, the normal lithologies. And, well, we found that there's a pattern there. Also, not claiming to understand exactly what this means. But what I'm trying to say here is that the Shapley values carry a lot of possibly valuable information. And there's a lot that we can do with it. So key takeaways, by combining this very accurate model with Shapley algorithm, we obtain better accuracy than all the benchmarks that we tested for, and we can, at least for deep learning standards, understand the model a little bit. And doing so has, well, two synergistic effects. One is that trying to interpret a very accurate model enables us to actually believe it a little bit, in the sense that if you interpret a model that had terrible results, then you won't, whatever the model learned probably wasn't something relevant. But if the model's good, you can get close to believing that what it learned may correspond with reality. So if you see that whatever it learned made sense, you're more likely to trust it. And the second effect is a bit more out there, as someone said yesterday, a bit like Obi-Wan Kenobi. So you would unveil new knowledge if you're studying a model that actually outperformed all other models, because it must have learned something new in order to achieve that outperformance. But again, with a lot of caveats, you need more of a holistic analysis here to actually see what the model learned corresponds with reality. So yeah, final words. Deep learning can be applied to even these niche fields if you apply the correct methodologies. Thanks for listening. And questions are welcome.
Thanks, Fabian. Time for one short question. Yeah.
Thank you. Very nice presentation. 2 questions. You were able. One
If you want a coffee.
you were able to show how this method works and validate it statistically. I was just wondering, how it outperforms other methods. What did it look like in a map or model? Did it give plausible results when you look at the interpolation?
Sorry, can you repeat? I couldn't catch everything.
Okay. So you were able to validate this method statistically. I was just wondering, this is an interpolation method, so it will produce a map.
Oh, yeah.
So what does that look like? Does it look like a nice map?
That's an interesting point. So in this study, I didn't show a full map because I needed validation to compare to other methods, so we needed to use the points that we had. We haven't generated a full map with it to see if it's believable in a way. But that's an interesting next step. We'll give that a shot.
But you won't have covariates at all the spatial location you want to estimate. So the comparison would be with the co-kriging.
That would also be the problem. We would need raster data probably in order to generate the whole thing. So yeah.
All right. Okay.
Thanks.
I'm sorry, but I think you can discuss over coffee. Thank you.